There is something profoundly wrong with 3I Atlas. Not wrong in the sense of malfunctioning or broken. Wrong in the sense that its physical properties defy what we know about how objects form and evolve in space. And the most striking of these impossible properties is something so fundamental that it challenges our understanding of material science itself. 3I Atlas reflects only 4% of the light that strikes its surface. 4%. To put that in perspective, that actually means something. Fresh asphalt on a road reflects about 7% of visible light. Charcoal reflects approximately 4 to 6%. Coal dust reflects about 5%. 3I Atlas is darker than almost any natural material we have ever encountered in our solar system. It is as dark as the darkest substances we can manufacture on Earth. And that single fact raises a question that no one has been able to answer satisfactorily. How does an object traveling through interstellar space for millions or billions of years end up with a surface darker than coal? Before I explain why this is genuinely impossible according to our current understanding of space weathering and surface evolution, I need to establish exactly what we mean by reflectivity and why it matters. When astronomers measure how much light an object reflects, we use a property called albedo. Albedo is a number between 0 and 1 that represents the fraction of incoming light that gets reflected. An albedo of 1.0 means the surface reflects 100% of light, like a perfect mirror. An albedo of 0 means the surface absorbs all light and reflects nothing, like a perfect black body. Most objects in our solar system fall somewhere in the middle of this range. Fresh snow has an albedo of about 0.8 to 0.9. It reflects 80 to 90% of sunlight, which is why it appears brilliant white. Earth's moon has an average albedo of about 0.12. It reflects 12% of sunlight. This is why the moon appears gray rather than white, despite being illuminated by the intense light of the sun. Asteroids typically have albedos ranging from 0.05 to 0.25 depending on their composition. Rocky asteroids tend to be darker, icy asteroids tend to be brighter. Comets, when they are inactive and not producing gas and dust, typically have albedos around 0.04 to 0.1. They are dark because their surfaces are covered with carbon-rich compounds and rocky material mixed with ice. Now here is what we know about 3I Atlas based on observations from the Hubble Space Telescope and ground-based observatories. The object has an estimated albedo of 0.04. 4% reflectivity. This measurement comes from analyzing how much sunlight the object reflects compared to how bright it appears. If you know the distance, the size, and the brightness, you can calculate the albedo using straightforward physics. Hubble observations in late 2025, when the object was relatively close and bright enough for detailed study, allowed astronomers to place an upper limit on the nucleus size of approximately 2.8 kilometers in radius, assuming an albedo of 0.04. That assumption of 4% reflectivity is based on typical cometary values. But here is the problem. The more we learn about 3I Atlas, the less it behaves like a typical comet. And if it is not a typical comet, then why should we assume it has typical cometary albedo? Let me explain why an albedo this low is genuinely strange for an interstellar object. Objects in space are constantly bombarded by radiation, cosmic rays, which are high-energy particles traveling through the galaxy. Solar wind, which contains charged particles from stars. Ultraviolet light, which has enough energy to break chemical bonds in surface materials. This constant bombardment causes something called space weathering. On rocky bodies like the Moon and asteroids, space weathering tends to darken surfaces over time. Fresh rock, exposed by an impact, is initially brighter. Over millions of years, radiation gradually breaks down minerals and creates microscopic metallic iron particles in the surface layer. This makes the surface darker and redder. On icy bodies like comets, space weathering also tends to darken surfaces, but through a different mechanism. Radiation breaks apart the molecular structure of ices and organic compounds. This creates complex carbon-rich molecules called tholins, which are extremely dark. Over time, a layer of radiation-processed material builds up on the surface, making it progressively darker. Both processes would make 3I Atlas darker over time. And if this object has been traveling through interstellar space for millions or billions of years, it has been exposed to cosmic rays and ultraviolet radiation from distant stars for an extraordinarily long time, much longer than any comet in our own solar system, which spends most of its time in the relatively protected environment of the outer solar system where radiation exposure is lower. So we might expect 3I Atlas to be dark. That part makes sense. What does not make sense is how uniform that darkness appears to be. Recent spectroscopic observations of 3I Atlas show something remarkable. The object does not just have low reflectivity, it has consistent low reflectivity across a wide range of wavelengths. From ultraviolet through visible light into near-infrared, the albedo remains remarkably constant at around 4 to 5%. This is unusual. Most dark objects in our solar system show variation in reflectivity across different wavelengths. They might be darker in blue light and slightly brighter in red light, or vice versa. This variation happens because different materials absorb and reflect different colors of light preferentially. But 3I Atlas shows what astronomers call a flat spectrum. It reflects roughly the same small fraction of light at almost all wavelengths we have measured. This suggests that whatever is covering the surface is not just dark, but uniformly dark across a broad spectral range. That kind of uniform darkness is characteristic of certain engineered materials. Carbon nanotubes, for example, can be manufactured to absorb 99% of light across all visible wavelengths. They appear almost perfectly black because their microscopic structure traps light efficiently at all wavelengths. Certain metamaterials designed for stealth applications also exhibit extremely flat, low reflectivity across broad spectral ranges. Now, I am not claiming that 3I Atlas is covered in carbon nanotubes or military stealth coatings. What I am pointing out is that achieving uniform low reflectivity across a wide range of wavelengths is actually quite difficult in natural materials. It requires a very specific kind of surface structure and composition. And the fact that 3I Atlas exhibits this property raises the question of how such a surface could form naturally. Let me give you another comparison that puts this in perspective. The darkest known objects in our solar system are certain asteroids in the outer main belt and some trans-Neptunian objects that have been heavily processed by radiation over billions of years. The darkest of these have albedos around 0.03 to 0.04. They are as dark as or slightly darker than 3I Atlas. But here is the key difference. Those objects formed in our solar system. They have been orbiting the Sun for approximately 4.5 billion years. They have accumulated radiation damage and surface darkening over that entire time while remaining in relatively stable environments. 3I Atlas is an interstellar object. It did not form in our solar system. It came from somewhere else. And based on its trajectory and velocity, it has been traveling through interstellar space for a very long time. During that journey, it would have been exposed to the intense radiation environment of interstellar space, much more intense than the relatively protected environment within a stellar system. But here is where the physics becomes problematic. Extended exposure to intense radiation should not just darken a surface uniformly. It should create variation. It should cause erosion. It should produce spectral features from the breakdown products of complex organic chemistry. We should see absorption bands from specific molecules. We should see variation in reflectivity based on composition differences across the surface. We should see evidence of the chemical processing that intense radiation causes. But we do not see any of that. The spectrum is flat. The albedo is uniform. The surface appears remarkably homogeneous in its darkness. This is consistent with one of two possibilities. Either the surface is composed of a material that naturally produces uniform darkness across all wavelengths, which is rare but not impossible, or the surface has been deliberately treated or manufactured to have these properties. Now, let me introduce another piece of evidence that makes this even stranger. Polarimetric observations of 3I Atlas, which measure how light is polarized after reflecting off the surface, shows something unprecedented. The object exhibits what astronomers call extreme negative polarization combined with a low inversion angle. Let me break down what that means. When light reflects off a rough surface, it becomes partially polarized. The degree and direction of polarization depends on the microscopic structure of the surface and the angle at which you observe it. By measuring polarization at different angles, you can learn about surface texture, particle size, and composition. Most objects show a pattern where polarization is slightly negative, meaning the reflected light is polarized perpendicular to the scattering plane at small observation angles, and then becomes positive at larger angles. The point where it switches from negative to positive is called the inversion angle. 3I Atlas shows two unusual things. First, it has an extremely deep negative polarization, much deeper than typical asteroids or comets. This suggests a surface made of very large particles with specific optical properties. Second, it has a very low inversion angle. The polarization switches from negative to positive at smaller angles than normal. The combination of deep negative polarization and low inversion angle is rare. It has only been observed in a handful of objects, and those objects typically have surfaces composed of large, porous particles made of mixtures of icy and dark materials. Laboratory experiments trying to reproduce this polarization signature have found that you need particles with very specific size distributions and compositions. The particles need to be large, on the order of hundreds of microns to millimeters. They need to be porous, meaning they have internal structure with voids. And they need to be made of materials that are weakly absorbing, like magnesium-rich silicates mixed with dark carbon compounds. That is a very specific recipe. And the question is, how does an object traveling through interstellar space for millions of years develop a surface covered with particles that have exactly these properties? Natural erosion and weathering do not typically produce uniform particle size distributions. You get a range of sizes from fine dust to large boulders. But the polarimetric signature of 3I Atlas suggests the surface is dominated by particles in a narrow size range. That kind of size sorting can happen through specific physical processes. On Earth, wind and water sort particles by size, creating beaches with uniform sand or gravel beds with consistent pebble sizes. In space, you do not have wind or water. But you could have other sorting mechanisms. Electrostatic forces during periods of high radiation exposure could segregate particles by size and charge. Repeated thermal cycling as the object passed near stars during its interstellar journey could cause surface fracturing that preferentially creates certain particle sizes. Or, and this is the possibility that no one wants to discuss openly, the surface could have been deliberately processed to have these properties. If you wanted to create a surface with very low, uniform reflectivity for observational or thermal management purposes, you would engineer a coating with specific particle sizes and compositions. You would create a porous structure to minimize specular reflection and maximize absorption. You would use materials that absorb consistently across broad wavelength ranges. And the result would look very much like what we observe when we measure 3I Atlas. Now, I want to be very careful about how I present this. I am not asserting that 3I Atlas has an artificial surface coating. I am not claiming it is a manufactured object. What I am doing is pointing out that the observed properties, the uniform 4% albedo, the flat spectral signature, the unusual polarimetric behavior, are all consistent with deliberate engineering, and they are difficult to explain through purely natural processes. Let me give you one more piece of context that makes this situation even more puzzling. We have observed two other interstellar objects before 3I Atlas, Oumuamua in 2017 and 2I Borisov in 2019. Oumuamua was unusual in many ways. Its shape was extremely elongated. Its albedo was relatively high, around 0.1, meaning it reflected about 10% of light. It showed non-gravitational acceleration that required some kind of outgassing or other force, but its reflectivity was not particularly strange. 10% albedo is high for a comet, but within the range of rocky asteroids. 2I Borisov was much more conventional. It had a clear coma and tail. Its albedo was around 0.04 to 0.06, typical for an active comet. Its spectrum showed water ice, carbon dioxide, and organic compounds, exactly what you expect from a comet. So, we have one interstellar object that was unusually reflective and oddly shaped, one that was completely normal and cometary, and now a third that is unusually dark with strange polarimetric properties and ambiguous activity. 3 objects. 3 completely different sets of characteristics. This raises a fundamental question about interstellar object populations. Are all 3 of these objects natural bodies from other stellar systems that just happen to have very different properties? Or is there something else going on? Is it possible that some interstellar objects are natural while others are not? Is it possible that we are detecting both natural comets and asteroids from other star systems and something else that is using those natural objects as cover? I realize that sounds speculative, but consider the evidence. 3I Atlas has a surface darker than coal with uniform reflectivity across all measured wavelengths. It shows polarimetric signatures consistent with engineered particle size distributions. It emitted radio signals matching prime number sequences. It exhibits non-gravitational acceleration without typical cometary activity. It has geometrically precise jet structures visible in Hubble images. It passed Jupiter at or very near the Hill radius, a gravitationally significant boundary. Every single one of these properties individually could potentially have a natural explanation, though some of those explanations require unlikely coincidences. But when you combine all of them together, when you look at the complete picture, it becomes increasingly difficult to construct a scenario where everything is natural and nothing is designed, the 4% albedo is not proof of anything by itself, but it is one more anomaly in a growing list of anomalies. One more property that makes more sense if the object is artificial than if it is natural. And when you start accumulating anomalies, at some point you have to consider that maybe they are not anomalies at all. Maybe they are features. So what happens next? Observations continue. Multiple spacecraft and ground-based observatories are tracking 3I Atlas as it moves through the outer solar system. The March 16th encounter with Jupiter will provide additional data about trajectory control and surface properties. Future observations will continue measuring albedo and polarization to see if surface properties change over time. If the albedo remains constant at 4% throughout the encounter, that suggests the surface is remarkably stable and resistant to environmental changes. If the albedo increases as the object moves away from the sun and cools down, that would suggest the darkness is related to thermal properties or activity. If the albedo decreases even further, that would be extraordinary and might indicate active surface processes we do not understand. The truth about what 3I Atlas is will emerge gradually through continued observation and analysis. But the albedo measurement, that simple 4% number, is already telling us something important. It is telling us that this object is unlike anything we have seen before from our own solar system. It is telling us that its surface properties are at the extreme edge of what natural processes can produce. And it is telling us that we should be very careful about assuming we understand what we are looking at, because sometimes the simplest measurements reveal the deepest mysteries. And an object that reflects only 4% of light, darker than asphalt, darker than coal, traveling through our solar system from another star, is asking us a question we are not quite ready to answer. What made you so dark? And why?